Hello everyone, good morning, and let's get started with our seminar today. And today it's my great pleasure to introduce to you Professor Zhao from Georgia Tech, Woodruff School of Mechanical Engineering, and the Institute for Robotics and Intelligent Machines. And we used to be colleagues at Georgia Tech for several years, and we collaborated, and I was always very, very impressed about his work, his new ideas in robotics, and I am sure he will share several of those ideas with us today. Professor Zhao is an assistant professor at the Mechanical Engineering Department of Georgia Tech. He received his degree, his PhD in Mechanical Engineering from UT Austin in 2016. Afterwards, he was a postdoc fellow at the Agile Robotics lab at Harvard University. And at Georgia Tech, he leads the lab that I just talked about, the Intelligent Decision and Autonomous Robots lab. And his research interests focuses on planning and decision-making algorithms of highly dynamic and contact-rich robots. He received several awards. I'll just mention one. That is a recent one, is the ONR Young Investigator Award last year. And today is my great pleasure to introduce him, and let's give him a very warm welcome.
All right, thanks so much, Galosio, for this nice introduction, and I always feel very honored and heartwarmed, to have like a former GT, very senior colleague, gave this introduction to me, and also thanks, Annie, having me here. So, okay, so today I'm going to talk about some of our recent works, especially on light navigation, and especially think about how to reason about agility, safety, and resilience performance, from the planning and the decision-making perspectives, and how to address some of the real-world uncertainties. So humanoid robots really have a long historical trajectory, that can be traced back to last 60s. And although there are still a lot of fundamental technological and scientific questions to address, like robot sensing, decision making, and behavior reasoning, learning, but there's no doubt we are really experiencing a great era of transforming these humanoid robots from science fiction to reality. And I think many people in this room probably seen some of these, well-known robots like Honda Asimo robots and Boston Dynamics Atlas. And right now we are at 2024. Tesla has been working on this Optimus humanoid robot for the past 2 years and really make great progress, impressing the whole community. Not only Tesla, over the past 2 or 3 years, there are more than 20 robotics companies really trying to build their general purpose humanoid robots that can really achieve, the task as our human can achieve or even beyond. And some people even call 2023 as the inaugural year of humanoid robots commercialization. I think the next 12 months is going to be very exciting periods for humanoid robots community, where there are going to be multiple robotics companies going to release their first generation humanoid robots. But I think there's still a lot of key questions to be addressed, like how functional this humanoid robot is going to be when they are first released, and there's still a lot of critical problems like battery life, safety, and cost, etc. So at Georgia Tech, as Galosio mentioned, I directed the Laboratory for Intelligent Decision and Autonomous Robots. We have a large focus on task motion planning, trajectory optimization, these days more machine learning algorithms for these highly agile robotic systems, mainly on the locomotion and manipulation problems. So we are particularly interested in how to design intelligent and robust algorithms for these walking robots navigate in complex environments, or even human crowd, and manipulation problems with irregular and deformable objects. So from a very high-level perspective, a fundamental research question we are interested in is what planning and decision-making algorithms do this lagged and the manipulation system needs to achieve very agile, robust, safe, or even collaborative behaviors and tasks. So in today's talk, I would like to mainly address two research questions. So first, I'm going to talk about how to design a hierarchically integrated task motion planning framework to better reason about the robustness and safety. And I think there are a lot of excellent work in the community provide formal guarantees on safety and robustness, but I think many times it's only guaranteed at the single planning and control layer. So really, when you have this hierarchical planning and control framework, this formal guarantees is often going to be broken. So in this case, how can we propose resilient and robust mechanism to enhance the overall task success rate and the safety? And although sometimes we cannot 100% guarantee or even prove it. The second question is going to about how to design or explore some locomotion and manipulation safeties in a principled way, especially for navigation problem in these partially observable environments or human crowded environments like a social navigation. Okay, so I want to use one slide to motivate a little bit, why task planning matters for navigation. And as we all know these days, these humanoid robots are increasingly demanded to be operated in more complex environments for more complex tasks, rather than just the level ground walking. So in this case, there are a lot of powerful task planning methods like symbolic AI planning, formal control method like temporal logic are very powerful to formally specify the task and synthesize decisions. For example, if you look at this Boston Dynamics Atlas robots, to achieve this task, hand over the bags to the human worker, it really have a long, horizon sequence that need to be accomplished. The robots need to build this wooden bridge first, and then step upstairs, and then climb this scaffolding, and then turn around and hand over the two bags to the human, and then push the box and then step down. Or maybe think about the digital robots. You need to visit this charging location infinitely often, or maybe alternatively, navigate between the rack and the conveyor belt to deliver the boxes. Or maybe there's a human shows up in the front, so the robot really need to come to a stop and yield for safety reasons. So this task planning framework is very powerful to make synthesize decisions with formal guarantees on safety and robustness or even provable correctness, and reasoning about long horizon autonomy and runtime assurance. But the question is why they are still largely underexplored, for the system. And probably, I think, as shown in the videos here, you can see, the robot dynamics are highly complex, and there are a lot of practical, hardware implementation issues, can make the system fail and become very risky or prone to failures. So in this case, the interplay between this high-level discrete task planning and the underlying continuous motion planning problems is going to be very important. So how can we guarantee the decisions from the high-level task planner can be successfully implemented by the underlying motion planner or controller, or can we encode some physical constraints from the underlying motion planner to the high-level decision-making process is going to be very important. So my group has been putting a lot of effort in this direction over the past few years. So here are some highlights of our TAMP framework for navigation. We explore this direction from multiple perspectives, including this whole body locomotion problems in these very confined, risky environments with some emergency behaviors. Also, the multimodal planning for this quadrupedal locomotion doing this rebar tying task in the construction site. We also have this heterogeneous robot teaming, including the quadrupedal locomotion system in hospital environments to do the task allocation and reallocation. So I would like to start with a very specific locomotion problem called push recovery, and leverage this example to discuss some design principles for task and motion planning problems. And for this push recovery problem, it has been a long-standing topic in the locomotion community, and people propose different recovery strategies, MPC-based foot placement planner, use different hip or ankle strategies to recovery, or maybe calculate the capturability region on the ground based on the kinematics and dynamic constraints. But many times, the environmental perturbation characterization is very simple and empirical. So sometimes they just have like a long bar, push the robots, or maybe have a ball, hand over the ceiling and then hit the robot. So very systematic characterization of the environmental perturbation and analyze its effect on the system stability is very important, but largely underexplored. And many times, people focus on the trajectory generation or the low-level control. So these push recovery frameworks often like high-level decision-making capabilities in response to diverse environmental events. And another thing is especially the light crossing behaviors is intentionally ignored because of the potential self-like collisions, which is very risky. Okay, so in this work, we basically aim to design safe locomotion plans that's going to be resilient to perturbation can happen at any time and any directions. And here I want to highlight the light crossing behaviors is actually important not only for the push recovery cases, and it's also going to be helpful in certain real world scenarios. So for example, think about a human walk across a river and there's like this zigzag type of stone in front. So naturally human need to initiate these light crossing behaviors to successfully maneuver over this terrain. Especially in the dynamic locomotion community, there are a wide variety of locomotion models people can use. We can think about from the left-hand side, very simplified reduced order model, like invertible model, all the way to the full order model on the right. In our study, we are more aligned with the simplified reduced order model sides, but with addition of the swing foot state where we can basically check self-collision components. And we focus a lot on the center of mass, robot center of mass dynamics. So we basically design our desired center of mass plans in the robot sagittal phase space and the lateral phase space. So here in this normal walking procedure, you can see these very periodic patterns. In the sagittal, you have this valley profile, and in the lateral direction, you have this limit cycle, for stable walking. And if you think about the essence of locomotion procedure, one of the most important thing is basically to design, where the robot's foot locations should be, right? So in this case, we leverage this reduced order model and design our motion planner. We call it a phase-based planner, which basically going to make decisions on the robot foot placement and the center of mass apex velocity, and where we call it a key frame state. So these are the discrete states when the center of mass is exactly on top of the foot locations. Okay, so in addition to that, our method can also quantify robustness. So in addition to this nominal phase-space trajectory, we also derive this graded regions, so-called the robust Riemannian regions. And these robust Riemannian regions can be calculated from using the analytical solution of the locomotion models and have the very nice closed form solution. So we can use this tangent cotangent manifold to do a discretization of the local keyframe space. And then we are going to use some temporal logic based approach as a high level decision maker to build dynamic transitions across these keyframe states and enable sequentially compose the multiple walking steps. Okay, so I would like to use just maybe one slide to give an introduction about the linear temporal logic. I'm just curious how many people in the room heard of linear temporal logic, if you have. Okay, good. We have some, maybe some not. Okay, I will give a very brief introduction. So you can literally think about the linear temporal logic as a formal symbolic language of rules and the symbolisms for specifying and reasoning about propositions in terms of linear time. So here we use this linear temporal logic method to make robot decisions in response to environmental events. And basically, we formulate it as a two-player game where the robots play the game with the potentially adversarial environmental player. And by following LTL's syntax and semantics, we can design a set of desired specifications we want the robot to achieve. And I will just give one example. If you look at the specification on the upper left, it can be interpreted as it is always true that when the keyframe state K is not equal to the steady state keyframe state KSS, then the next walking step, or at the next walking step, the keyframe state need to recover back to this steady state. Okay, so this specification basically indicates a very common or popular locomotion, heuristics people use. So people usually require, when the robot is perturbed, it need to recover back to the normal case, within 2 walking steps. And this is just one simple example. You can actually follow the LTL syntax and semantics and specify a list of, desired, safety and liveness specifications as you want. And then you can throw these desired task specifications to some, off-the-shelf solvers. So here we use Slack. You can use others as you want, and basically synthesize a decision maker offline. And then during the online phase, we can detect the current keyframe states, and then query this this keyframe decision maker online, and then predict the future keyframe decisions. So then we integrate this LTL-based synthesis automata to the higher level as the decision maker. And then the environmental perturbation from the terrain, from the treadmill, is going to be characterized as the external perturbations. And basically this environmental perturbation is going to try to falsify the robot decisions. And here we use this LTL-based reactive synthesis to make decisions, for the robot to recover from these external perturbations, and by making decisions about the robot's foot locations and center of mass apex velocity. But this only happens at the discrete time, like the discrete, keyframe state. So you might be curious, okay, what about the perturbation that can happen at any continuous time? So in this case, we have another middle layer behavior tree that can make local online modifications, to handle the perturbations that can happen at any continuous time. And then this decision behavior tree is going to send the updated decision sequence as the hyperparameters to the underlying trajectory optimization for the whole body motion generation. And overall, for this hierarchically integrated TAMP framework, we have 2 robust mechanisms. So first one is the LTL reactive synthesis, use this remaining robustness region, and then the behavior tree have this replanning mechanism for robustness quantification. So we evaluate this hierarchically integrated TAMP framework on our carrying system. This system is actually originally designed for human clinical and rehabilitation studies. And this treadmill on the top is actually sit on top of Stuttgart's platform, so it can exert 6 dimensional perturbations, X, Y, Z, rho, pitch, yaw. And this is a very nice platform where we can systematically study the perturbations and how human or robot can recover from these external perturbations. And here I show 4 different cases. With each video gives you a specific perturbation direction. And if you look at the upper left one, the 0-degree perturbation actually going to involve leg crossing behaviors. So the leg is going to cross about 8 centimeters in the lateral direction, which is a very challenging task to achieve. At the lower level, we use this so-called passivity-based whole body controller. And for the figures on the left, it shows this sagittal phase space. On the right-hand side, we show the lateral phase space. And in the normal walking case, the first row, you can see it shows this very nice, periodic patterns. For the sagittal, you have this valley profile. In the lateral direction, you have this limit cycle. So this is a perturbation-free case, just in the normal walking case. And then we have the lateral perturbations. You are going to see the lateral phase space is going to either use take a larger step or maybe the leg crossing behaviors to recover from these external perturbations, and then finally reach to the limit cycle steady state. And in all cases, you can see our low-level whole body controller performs pretty good and do very well center of mass tracking. Okay, so this is good. But there is one problem for this hierarchically integrated TAMP framework. the first thing is, this LTL reactive synthesis actually require a discretization of the center mass state space, and we can only design the keyframe states in this discrete space. And this discretization naturally introduces a gap between the discrete high-level task planner and the continuous underlying trajectory optimization. And then the second problem is, as I said, we have two robust mechanisms, but they are crossing two different planning layers. So in this case, we can really not provide formal guarantee on robustness, when we have this, cross layers set up. And then the question is, if we can have any more advanced method where we can have a more unified robustness quantification and better, robustness semantics reasoning, maybe in a more continuous way. So this motivates our more recent work using signal temporal logic approach to directly reason about robustness semantics in the center mass state space. And here we transform the STL specifications as the robustness degree, and we encode it as a cost function in our MPC controller, which actually run in an individual layer. So in this case, we can directly reason about robustness without loss of formal guarantees that, if we cross multiple planning layers. And also, this STL MPC framework has a data-driven constraints for the self-like collision avoidance, and it's actually solved, super fast and very accurate. So I'll show some result in a second. And let's take a look at how this MPC framework works. So basically, in the cost function, we have this penalty on the control effort, LU, and it also have additional robustness degree score, this rho. And which basically means we are trying to maximize this robustness degree, which is equivalent to say we are going to maximize the task specification satisfaction. And then if I give you like a stable locomotion specification here, so which basically means finally I'm going to let my keyframe states stay within the Riemann region at a certain timing interval. So this is actually not the next immediate walking steps. We are enforce it in 2 walking steps. And then there's some additional specifications for the reachable foot locations. There are kinematics constraints. And we identify this as the total locomotion specification. We can transform this into this robustness score by using this STL encoding method. And basically here we say if the robustness score is non-negative, then the task is satisfied. And if it's larger, and it's better. It have more robustness. So here the goal is basically we want to maintain this keyframe states within this gridded area, this Riemann region. So this is similar to the previous hierarchical TAMP framework we have. But here we are going to use this cost function to really push this green dot, this keyframe state, close to the center as much as possible. Okay, and this is also a big difference from the previous hierarchically TAMP framework. So in that case, in the previous case, once the state is outside this Riemann region, the LTL cannot really figure out any solution. But here you have these states, even it's outside this Riemann region, we can still solve optimization and keep pushing it back for task satisfaction. Okay, questions?
What does the rule look like? Does it have integer variables?
It's in this case, it's a continuous. I'll talk about it in a second. So in the traditional way, people will encode binary variables for this case, but it actually causes a lot of problem for solving this optimization. So in our case, I'll talk about it in a few slides. We actually transform this rho to a continuous value, so you can leverage the gradient-based optimization approach. So it's a continuous value. Yeah.
What about W that you choose?
W is like a weighting coefficient, so you can weigh the importance between the control effort and the robustness satisfaction. So usually this is some parameter people, the designer gave some option, but it definitely, tune this W parameter will influence the optimization performance as well. Yeah. Okay, good. So, and for this self collision avoidance. So we basically use this very standard multi-layer perception module to calculate the distance between different geometric pairs. So for Cassie slag, it literally have 4 different geometric pairs that the collision can happen, and we then encode this MLP as a self-collision avoidance constraint into our MPC problem. And it turns out that this can solve, super fast. Basically, it's approximately like 1,000 times faster than the standard IK-based approach. So, this traditional IK-based approach can solve maybe like 1 kilohertz, and in our case, we can solve like 1 megahertz. So, which is super fast, and also to give us a very accurate solution. So, roughly, on average, the absolute error is about 2 millimeters. So this is actually one big component, to make our MPC can be solved in an online fashion. So we did a lot of systematic tests, for this push recovery from omnidirectional perturbations. And here I show this spider graph. So basically, this graph showing the maximally tolerable disturbance, the robots can withstand. And here we have 434 trials. So we try perturbations from 9 different magnitudes, 12 different directions, and also 4 different locomotion phases. So each spider graph corresponds, a specific locomotion phase, 0%, 25%, 50%, and 75%. And here I show 3 different approaches. So the blue area is our STL MPC. And then the A-leap controller is the red region. So it's basically a angular momentum-based linear independent model from Michigan, Grizzle's group. So this is one of the state-of-the-art controller people use for Cassie robots. For the LTL controller, this is our previous hierarchically integrated TAMP method. So we can see in all cases, our STL MPC actually outperform than the 2 baselines. And especially if you look at the left half plane, our approach is actually significantly outperformed than the other 2. This is because in this left half plane, there's going to be line crossing behaviors, and the A-leap controller baseline doesn't have this self-collision avoidance capability. So let's take a look at, yeah.
I guess I'm trying to get a handle on exactly what is making it better than the other approaches. So there could be 2 possibilities. Like one is maybe the STL part. Since you're taking into account like a longer horizon plan,
right.
Like maybe that's what's giving you the robustness, or the MPC part, right? That you're reasoning about like dynamics at a higher fidelity than the A-leap controller, which is just thinking of the system as a linear pendulum. I guess I'm wondering if we compared this against like a control barrier function method that took into account the full dynamics of the system, would you still get a benefit from the STL part, or I don't know if you've done those kinds of comparisons?
I think that's a good question. I think for our methods, I think we outperform because of 2 reasons. One is, as what you said, we are considering 2 walking steps in the future, not the next immediate step. And this, our previous LTL controller, because it's based on the reactive synthesis, is only reason about the next immediate walking step. So, longer horizon definitely help us to, have a little bit more flexibility to recovery, because, sometimes the robot cannot just recover within 1 step. It really needs 2 steps. So that's what our framework can give us. And then the other thing is about the robustness. So this robustness region is the key thing. So even it's a fail outside, we'll try to push it back. This optimization-based approach is really helpful. Compared to the A-leap model, because they, by default, they really don't have this self-like collision avoidance. I guess if we sort of encode, using some like, control barrier functions, you can achieve it. That's possible. But because the lag really have multiple geometric pairs, so we still believe, using this data-driven approach is much more efficient to make things can run online. So I think that's the 2, critical pieces make our approach perform better. Yeah. Okay, so let's take a look at how it looks like really on the Cassie robots. And we show 3 different cases. Our approach compared to the baseline. So in all 3 different cases, you can see, we can succeed and the baseline approach fail. When we have this 180-degree perturbation, in this case, the 2 approach perform very similarly. So our approach is a little bit better. So if we exactly apply this, perturbation here, our approach can succeed and the baseline will fall. And then if you look at the 0 degree, which is the challenging case, which is going to involve the line crossing behaviors, and this is a clear win situation for our method. And then we also do the forward push. Both of them have roughly similar performance. We can also do locomotion over stepping stones, and here we can encode the logical constraints, these 5 stones, so to identify the potential, stepping stones for the robot. And in the presence of these external perturbations, it can recover back from these, external perturbations. And this is going to be answer, your question about this rho value thing. We also compare the computational speeds between our method and the traditional mixed integer programs. So traditionally, when people solve this STL method, they will encode the specification into the trajectory optimization by introducing boundary variables, which could be very computationally expensive due to the large number of boundary variables you have. And in this case, we avoid these boundary variables by using this so-called smooth approximator method. So we basically use a list of approximation functions, this like log functions to, remove this min-max operators, which basically non-differentiable, and to give you like a more smooth, kind of quantification for the robustness. And then this is very, useful for us to speed up. And overall, it makes the performance, our approach is, a little bit, 5 to 10 times faster than the traditional MIP approach. So this is also one big part to make our MPC can be solved online around 30 hertz. Yeah. Yes.
So I have a quick question. What happens to your guarantees when you replace your min-max signal temporal logic by this smoothed out version? Do you retain any guarantees, or are you sort of
yes, so there's some theoretical analysis when you replace, it's an approximation method, but I think there was some theoretical study you can still get this soundness kind of, approach, and so it is an approximation, yeah, but it's a very, I think close to what we can perform using this traditional approach, regardless of the computation time. And from our locomotion perspective, it's practically speaking, it works pretty good. Yeah, but there's some theoretical studies there. I can send you some reference, afterwards. Yeah, yeah.
I guess, why have it in the cost instead of as a constraint?
That's a good question. You can do in that way. Well, basically, you can think the cost function is maybe a soft, way to enforce your constraints as you want. But yeah, naturally, well, there are actually some constraints for. Well, this is more like details about this. So when we calculate this rho tilde, it's not just a single scalar because we have multiple, task specifications. There will be. No, not this one. Yeah, there will be multiple, rho values, and there's this min-max operator I mentioned, and then we apply this smooth operator method. So we are going to, select the, the mean or the max using some approximate functions, and these functions are actually encoded as a constraint. I didn't show it here, but there's kind of a constraint you can enforce. But in general, I think your question is. You try to enforce maybe this rho value as a constraint, maybe larger than 0.4, 0.5 as you want. We really haven't tried in that way, but I think in principle, I think the solver can give you some solution. But sometimes it's very hard to enforce the constraint because you really don't know what is the desired rho value you want, because the perturbation can be random. So we just rely on the cost function to push it to the maximum value, yeah, to our best. Yeah, That's a good question. We might try it out. Go back, see how it perform. Okay, good. So, okay, I'm good. This. So we also ran the test on the inclined stationary surfaces. So in this case, the contact surface is maintained at a certain slope. And we have this horizontal, perturbation applied on the robot's center of mass, and we can see the robot perform good. And this is another test. We have this orientational perturbations, on this dynamically rigid surface. So you can think is, the robot is walking kind of on a boat, in the sea, and in this case, the A-leap controller fails, so we can do other types of benchmarking, to show the advantage of our approach. So I want to talk a little bit about the hardware experiments. The current system I mentioned earlier actually cannot push the Cassie robot to failure because of the system itself has some physical limitations out of our control, and it cannot really exert too large perturbations to make a Cassie fall. And then in this case, we actually use another system called the BumpAm system. So it's a perturbation emulator system originally designed by Steve Collins' lab. So they open sourced the hardware, and we one of my neighbor colleague, Greg Sawicki, so his group built one, and then we use this to exert larger perturbations on the system. So it's a very, very simple system, simple mechanism. So you have this, it's basically a pulling system with a motor on the rail on the back end. It have this force sensor can accurately measure the force, applied on the cable and pull on the Cassie robot. But it's enough, it's sufficient to apply very large and accurate perturbations as we want from omnidirectional perturbations. And here we show 8 different directions perturbations. And the goal here is again to estimate what is the maximum tolerable perturbations that can be applied on the robots. And this is the data we have, so it's the spider graph, and you can see especially on the 0-degree perturbation, it have the smallest tolerable magnitude because this part involve light crossing. And roughly this hardware results match very closely to what we have from the simulation. And we also do orientational terrain perturbations along single axis, so either through the pitch angle and the roll angle. And in both cases, we can tolerate up to 5-degree orientational perturbations in this case. And there are 2 actually interesting observations. So for the pitch axis perturbations in the first video, there's actually a very clear pattern about the stepping frequency correlating to the uphill or downhill locomotion scenarios. So when the robots walk uphill, the stepping frequency is going to be increased because there's always going to be an early contact happen. And then when it walk downhill, because there's a late contact, and the robot's always going to stretch out its leg to make the contact, so the stepping frequency is actually reduced. For the lateral perturbation case, there are actually a lot of leg crossing behaviors if you see closely. This is actually a very challenging task to achieve because the treadmill always try to push the robot from the steady states. And this is another way to highlight the importance of using, incorporating these leg crossing behaviors in our approach. We also do this dual axis rotational perturbations. So we have a roll and pitch applied at the same time. This is probably the most challenging test we run. And it can tolerate up to 4-degree perturbations on this platform. And this is the most challenging case, at least from our perspective. And I think I believe I show some nice looking videos. I do believe it's necessary to show some critical failures. Just give you a sense, how challenging this problem is, and and especially for these push recovery problems. And these are the scenarios my students have to deal with, many hours before they really get a good result I showed earlier. So basically, we identify 3 types of critical failures. So the first one is basically when you apply 2 large perturbations, the robot is going to fall. So this is a very obvious. And then sometimes we see the robot step outside the treadmill, and this is likely going to cause a failure. Well, if the robot come back by some chance, it can recover, but it's not guaranteed. And also, the robot also have this gantry harness rope, for safety reasons. And sometimes we see this harness will pull the robot and will cause failure. So there are a lot of experimental effort, basically over the past 3 months, and my students spent a lot of time, understanding, how the system works and how the robot have physical interactions with this dynamically changing surface. And I want to give, a credit to my students, Zhao and his team, and also a special thanks to Jenny and Greg for their supporting on the carrying and bump arm testing. Okay, good. So let me see. So on the second part, I'd like to discuss some principled ways about how to explore locomotion and locomotion and navigation safeties in this partially observable and human crowded environments. And here, the central question we are interested in is how to guarantee robots, multi-level safety in this partially known, partially unknown environments, and at the same time achieve more complex tasks, as those seen in the autonomous mobile robots, but probably in a more like outdoor and more complex environments. And there are several key, considerations. The robots need to consider not only navigation safety, but also locomotion safety. And the robot need to avoid collisions with, dynamic obstacles in the environment, and also you need to choose the right photo locations for balancing. And the environments could be, complex. Usually, it's going to have, rough terrain features, partially observable. Environments, and there could be, humans shows up in the environments, and there could be a lot of uncertainties. So in this case, how we are going to parameterize and characterize the environments is very important. So we're going to use fine or coarse level abstraction. So this is all going to give us very different, computational workloads and planning capabilities. And the last but not the least, the robot always want to, collaborate with other robots or humans for cooperative tasks. So in this study, we aim for safe locomotion in these partially observable environments with dynamic obstacles in the environment. And here we use this little quadruped treated as adversarial environmental events. And to enable safe locomotion in these environments, again, we leverage our reduced order model phase-based planning, where we can make decisions on the robot's photo locations and the center of mass apex velocity. And given this reduced order model, we can have a list of locomotion safety criteria. Here I won't go through all the mathematics. I'll just give you, 2 quick examples. So there's one safety criterion. You can say the apex velocity between 2 consecutive walking steps difference is going to be bounded by the step length. So it basically means, if the robot walk, it knows the next step length, and they know its current apex velocity, then the next apex velocity is going to be bounded. If it's too large, the robot is going to fall down. Okay, so this is very intuitive. And then the other safety criterion is the turning angle. So basically, the turning angle is bounded by your apex velocity. So think about, the robot walk forward at a certain speed. If you want to make a turn, the turning angle cannot be too large. If you turn too aggressively, the robot is going to fall down. Okay, so I hope this is very, straightforward. And then the key part is we encode these safety criteria into the high-level task specifications. So in this case, we can guarantee the high-level task specifications can be successfully, executed by the underlying motion planner. And this is, I think, there's a big difference between, lag navigation and, traditional navigation problems for grounded mobile robots. Here, we have to seriously think about the underlying physics and the underlying dynamics, how it's going to pose additional constraints and limitations in the high-level task planner decision. And here, we have this hierarchically integrated TAMP framework for lag navigation on the higher level. The navigation planner is going to guarantee navigation safety, basically avoid collisions with other dynamic obstacles, and it can have other specifications like visit a specific location infinitely often. And then this high-level task planner is going to calculate a sequence of locomotion actions and send it to the middle level motion planner, the phase-based planning we already talked about. It have this capability of 3D maneuvering and rough terrain locomotion capabilities, and then send all the way to the low-level control for checking. But then there may be one question you will ask. The environment could be complex, and sometimes you might not have a full knowledge about the whole environments. And then in this case, how the robot is going to make decisions about where to move next without knowing the full knowledge about the environment. So in this case, a very natural choice is to reason about the environmental observability. And here we design a simple belief abstraction method which can dynamically track the potential obstacle locations, even when these obstacle locations are out of the local settled view of the ego robot, which is Cassie. And this abstraction is designed by partitioning the global environment into multiple local belief regions, and we dynamically make the belief updates according to the new observation, local observation from Cassie's side. And then from the high-level planning perspective, we again formulate this problem as a two-player game between the robots and its environment. And here, these grounded mobile robots are treated as adversarial environmental events, and it's actually try to falsify the Cassie robot's behaviors. And here, the Cassie robot is required to start from the pickup location upstairs and go downstairs and go to the destination for delivery, and at the same time avoid collisions with any other mobile robots in the environment. And here you see the colored map is online updated belief according to the Cassie's local field of view. We also test this on our new humanoid robots digits. We also do a more like kind of a full stack task where the digits robots need to pick up a box from the rack and then turn around and then climb stairs and deliver it to the destination upstairs. Let's see the time. Okay, I think I'll maybe speed up a little bit. So there's also a very common limitation in this traditional signal temporal logic approach, where many times people pose very strong assumptions about the environmental states, and which is maybe not really consistent with the real physical world. And in this case, we design a new method that can explore or leverage the different robot capabilities of the heterogeneous robot teaming to resolve some of these environmental conflicts. And here you can see if there's a drone trying to fly through this region, and then it doesn't really have the capability. It detects the door in front of it only at the runtime. And then it's going to send a assistance signal to digits and ask a digit to push the door, open the door for the drone. And then the drone can fly through it and digit can resume its original task. So to resolve this environmental conflict. And here we propose a replanning strategy to detect and resolve these unexpected environmental failures by leveraging, we can say, resynthesis, other agents' decisions at runtime. So this is just one proof of concept. We're actually targeting more complex, scalable, safe motion, task motion planning in this case. So we have a Eros paper submitted a few days ago. It solved like a small problem for this big scenario. So we are targeting heterogeneous robot teaming with manipulators sort object into the box, and then the Cassie robot is going to pick up the box and deliver it downstairs. There could be like the drone system flying through. And we're especially solving, when under certain situations when the LTL specifications cannot be satisfied due to, the robot capabilities, limitation, or maybe the environmental constraints. So in this case, how we can still try to, satisfy the task as much as we can and get a minimally violation solutions here. So this is a fairly complex, setup. We have not solved the full problem here, but we are on the way there. Okay, so I want to talk a little bit about this new work on the social navigation, maybe 2 or 3 minutes. So basically, think about when the environments have not only passive robots moving around, but also like humans. So in this case, how can we design socially acceptable trajectories, in these human crowded environments? And in this case, we leverage this conditional variational autoencoder approach to predict both robots and pedestrian navigation paths in the future. And here in this whole framework, we have two network modules. So we have the pedestrian prediction network, we have the ego agent social network. And these predicted trajectories for both robot and humans actually characterized as a set of reachable sites, which are parameterized by zonotopes. And then we encode these social zonotopes into the robot's MPC planner as a geometry constraints. And here we have this season MPC, which is a social zonotope network-based MPC. And basically using this zonotope representation enable very efficient collision checking, and we can also reason about uncertainties from the model discrepancy perspective. So this is a collaboration with Shreyas Kaushik, who just joined our school recently. So we basically have two network modules. So on the left-hand side, we have this pedestrian prediction network. On the right-hand side, we have the ego agent social network. Let's see, I'll speed up a little bit. So, I can talk a little bit more details here just quickly. So this sign dot on the upper left represent the ego agents, and then the green dots are representing the surrounding humans. And then the yellow stars represent the goals of these pedestrians trying to target. And this CV architecture take these goal positions and the past, the previous, observations of the pedestrian's path, and also the next ego agent's actions as the inputs. And then it will predict a set of zonotopes for the pedestrian future path. And then it will send these zonotopes as an input to the ego agent's social network. And this have a very similar CVAE architecture, and then it's going to output a zonotope for the ego robots. And in this case, the navigation safety is rendered by this so-called socially acceptable zonotopes. And one thing I want to mention is there's actually a collective effect of the surrounding pedestrians, which is actually taken into account in this ego agent's future trajectory prediction. And here we aggregate the summation of this surrounding pedestrian zonotope. And on the other hand, the prediction of the pedestrian's future path is also conditioned on the ego agent next action. So here we are really creating a coupling between these two networks. So in that case, we can have like a joint prediction of both the ego agents and the pedestrian future trajectories. We also encode some STL specifications. These are very similar to the ones I presented before. The locomotion apex velocity should be bounded, and the heading angle change should be bounded. I'll not maybe talk too much. One thing I want to mention briefly is this robot specification is important because when we learn the neural network, we all use the real human data set. But this data set might not be applicable to the robots. So we really need these robot specific specifications to make sure the trajectory we generate is going to be dynamically feasible on our digit humanoid robots. And then finally, we encode this social zonotope network into this MPC planner as the constraints. I think I'll speed up a little bit and give you the results. So these are some of the preliminary results we have, and you can see our framework can generate these socially acceptable trajectories, and we do a lot of extensive simulations, and they have this very consistent speed and similar safety performance as other. We actually do the CBF version as well, so very similar performance, and we run the dynamic simulation in the exact same. And we are actually working on the hardware part to see, evaluate the real performance. I think I will skip this. Another big part of my lab is on trajectory optimization. I don't think I have time to talk about it, but we actually focus a lot on how to design risk-sensitive cost functions to reason about the contact uncertainties and encode this as a cost function in the trajectory optimization. And the other one is about how to use distributed trajectory optimization to achieve better consensus work. Just very quickly, if you have this, large-scale nonlinear program to solve, including whole body dynamics and toroidal dynamics, this problem, can be super complex. Just look at, this, how long this constraint list could be, and how many numerical problems you can have. And the question is, can we explore some internal structure of this large-scale nonlinear program and to solve it more efficiently? And then we propose a alternating direction methodology alternate between the centroidal dynamics and whole body dynamics and solve it, iteratively until dynamic consensus. I'll just show some videos. The robot can do all different kind of cantering, parkour, and zero gravity reorientation. We also tested on the mini cheetah robots where do this 180-degree twisting in a very dynamic way. We can generalize this to manipulation problems, and you can have more blocks in your problem. So basically, you solve like 80 mm problem, and we can have like more deformable context modules in this MPC problem. This is maybe the last two slides I will show. So we also work on a new sensing-rich humanoid robot avatar with this soft super limb arm on the top. And we also have peripheral sensing modules like the tactile gel set sensors at the fingertip and this morphological reconfigurable robotic limb as a new robotic foot. And there are a lot of new sensors and kind of design, sensor integration, fabrication procedures we have to go through. And this is a new foot, which actually have two tarsal segments on the sides. It's actually inspired from the animal goats in nature. And we have 5 different sensors integrated to do the terrain classification and collect rich context sensing information. We are also designed the cleats on the foot, to increase the traction with the terrain. This is a new small robots. We actually collaborate with USC, and we're actually starting this direction in parallel, so to analyze how the robots can navigate in this granular media like poppy seeds. So there, we collaborate with people from physics. They study the terrain, terrain dynamics. I think I'll maybe end up with this slide. So I think as we move forward, we are really getting close to think about deploying a team of robotic system, to do more practically useful tasks. Although there's still, technical challenges we need to, to handle. But hopefully, over the next, 1 or 2 decades, we can really see this walking robots, show up in our daily life and change the way, we work, we live, or maybe entertain. So with that, I'm going to stop. And thank you everyone for your attention. Yeah.
Thanks, Ian, for a very nice presentation, and I think we can take a few minutes for questions. Maybe a couple of questions before we end. Jaime?
Hi. Thanks, Ian, for the super interesting talk. I have a lot of reading to do after watching this, and I very much look forward to telling to you in a bit more depth. But I was wondering, I have a specific question regarding the cool example where you were showing the motion platform and you were changing the slope dynamically while the robot was walking, and you were saying that one of the main sources of failure that you detected was just when the perturbation was too large. And I'm curious because you have this signal temporal logic reasoning sort of being computed all of the time. To what extent do the failures, like sort of the thresholds that would trigger a failure, align with what your prediction would be from the STL? And can you turn this, or is there a way to turn this into a certificate so that you can, ahead of time, determine these are the conditions that the robot is able to handle with this controller? Yeah. That's a good question. I think from our hardware experience, at least as long as there's a keyframe, this robot's center mass keyframes stay within this Riemannian region, I think we can 100% claim the robot is going to successfully maneuver and recover from the the perturbations. But the failure actually comes from when there's like large perturbations, when this state is pushed outside these Riemannian regions, and we have a better chance to recover back. But in this region, it's a little bit hard to guarantee because the real world perturbation is very diverse, and we don't know where the center of mass is going to push to. And this is a kind of like a
a kind of like a very open question. And here the perturbation we are addressing is very, kind of omnidirectional, different locomotion phases, so very diverse. And I think, the STL definitely help us a lot to, quantify this robustness and push things, back into this Riemannian region in a very timely fashion by solving this MPC in an online fashion. In terms of the certificates, different approach, and I think this maybe also go to the question if you can encode this as maybe a constraint, CBF constraint. I think the potential is there. Just so far we haven't done any, comparison along this line. There may be other better ways to maybe kind of achieve a similar or maybe comparable performance, I guess, but we really haven't tried anything along this line. Maybe that could be the next interesting topic, to look at. But another thing I want to point out is our MPC can be solved, very fast, as I already mentioned a few times. I think this is another critical piece, for our successful recovery. Because if the MPC solved, even from 30 hertz to just 5 hertz or 10 hertz, the recovery performance is completely different. Sometimes if you don't solve it fast enough, it doesn't have time to really recover within timely. So that can also cause a big problem. So I would like to say our data-driven self collision avoidance constraints and also the smooth operator method really make the MPC solve fast enough for our purpose. Yeah. I'm not sure that answered your question, but
no, I think it does. Like I say, I think it's just an interesting open question and something that would be useful to do, right? Because it's a bit of a catch-22 if you're saying, the controller will guarantee that it will maintain safety if we stay in this Riemannian region, right? But how do we know if we'll stay in that Riemannian region, right? So you need to sort of zoom out and give some kind of guarantee that states under what conditions you'll actually stay in there. Because at the end of the day, it is an invariance property that you you're replacing one invariance constraint by another, but it still doesn't answer the
So right now, the Riemannian region was kind of selected empirically right now. And we actually look at the human data. Actually, our collaborators have the real human data. So we can, because Cassie roughly have the same size of a human, the pelvis height is similar. And then we designed that Riemannian region sort of using a little bit sort of inspired by human, recovery capability. But I guess they're more like, kind of certifiable way to quantify the robustness margin. Yeah, if we want.
This is great.
Yeah.
Any pressing final question?
Well, I guess I'm curious to hear your thoughts on reinforcement learning-based approaches to these kind of problems. I mean, maybe looking 5 to 10 years from now, do you think that one of the approaches, like model-based versus RL, will win out? Or we will have some sort of hybrid thing? Or just curious about your thoughts.
What is the future?
Yeah, this is the future, and we actually also have some RL work I didn't get a chance to present. I think so. We kind of explore some problems like the robots maneuver over rough terrain, and we are using some inverse RL problem to not only learn the policy but also learn the rewards. What are the important features for this locomotion procedure over rough terrain? I think long-term run, I feel, this RL is really dominating these days. And I think I'm trying to see, from my perspective, I think we will use RL when there's a need. It's not just I think naively you have some maybe, model-based trajectory optimization give you some demonstrations and then you use it for RL or maybe imitation learning. It's more like how you can loop in things together. Like this last trajectory optimization part I mentioned, this distributed trajectory optimization. We are actually thinking about how we can integrate model-based trajectory optimization with RL policy together. And it's not just in one way, like hierarchical way you solve the problem. It's more like looping things. So the policy you learn from RL can also maybe inform your model-based trajectory optimization for better solution. And then overall you have this model-based and the RL approach to achieve better consensus overall. I think that's my philosophy, and I feel the contact part is also very challenging to solve, in terms of RL. So how to solve contact-rich manipulation locomotion problem using RL? I think there are still a lot of work to do. I'm not sure this domain randomization approach can really solve the things, from a fundamental perspective. But I think there are a lot of work we need to think about deeply from a more principled way. Yeah.
Right. Thank you again, Ian, and let's thank him for the very nice seminar.
Thank you. All right. Thank you.